connected to the output, able to handle high voltage. Hello, I'm Flavio, and today we're going to take an important step further, mostly on the theoretical side. Don't worry though, in the next video we'll return to experiments, and a very interesting one. But before moving on, let's briefly recap what we already know from the previous video. In this experiment, we saw that when we combine a coil, a capacitor, and a spark gap, the system responds with short bursts of oscillation at a well-defined resonant frequency. The spark gap itself does not set the frequency, it only provides a fast excitation. After that, the circuit evolves according to its own resonance. Part of this energy can then be transferred through the magnetic field produced by the coil. We also introduced the concept of self-capacitance. An insulated metal body has capacitance with respect to its surrounding environment. This turns out to be critical, at least as important as the resonance itself. In practice, these two aspects always appear together. We then saw that two coils placed close to each other and magnetically coupled can exchange energy even when they have very different number of turns. Under the right conditions, this can result in very large voltages appearing on one side of the system. Finally, we saw that resonance is a fundamental requirement. Without proper tuning, especially at low power, it becomes very difficult to obtain strong effects. At this point, it should be clear that resonance, not raw power, dominates the behavior of these systems. To keep pushing forward, it's useful to start from something familiar, the electrical transformer. In its classical form, a transformer consists of two or more coils wound on a common iron core. In this configuration, the behavior is well understood. Strong magnetic coupling, low frequency, and a clear voltage relationship between primary and secondary. But what happens if we remove the iron core and at the same time increase the frequency? At first, it's tempting to keep using the same formulas. Interestingly, it is precisely when coupling becomes weak that the transformer picture starts to lose predictive power. The problem is not that these formulas are wrong. The problem is that they describe a very specific limit, strong coupling, and we are no longer operating in that limit. So, what do we do instead? One extreme case is strong coupling. In this limit, the two coils behave almost like a single object, and the transformer picture works well. The opposite extreme is no coupling at all. In that case, no energy transfer is possible though, and the system becomes uninteresting. What we are interested is in the region in between. Tesla-type systems operate in this intermediate regime, where coupling is deliberately reduced. Energy transfer becomes slower, but this allows resonance to build instead of being suppressed. With strong coupling, the primary tends to control the secondary. With very weak coupling, the two behave independently. In between, the primary no longer controls the secondary, it excites it. This means that the coupling is strong enough to allow energy to be transferred, but not so strong as to prevent the secondary from behaving as an almost independent resonator. This is essentially a sweet spot. In practical Tesla coils, this typically corresponds to coupling coefficients on the order of about 0.2 to 0.3 of K value. At this point, resonance, not transformation, becomes the dominant mechanism. This reframing already explains several experimental observations. It explains why weakly coupled systems can still produce very high voltages. It explains why tuning is so critical, and it explains why geometry plays such an important role. Why it does not yet explain is how this resonance exists in space. These are not details, They are central questions, and to answer them, we need to look more closely at the spatial structure of resonance itself. Anyway, I hope you enjoyed the video. Feel free to comment here below. See ya!